So hello everyone, welcome to StudyMate Physics class one more time. And today we will keep learning with this effects of forces, and we'll continue with the Hooke's law. Hooke's law states that the extension of a spring is proportional to the applied force. So this extension of a spring, this extension, we call it X, is this proportional to the applied force. So from that comes the formula F equals K times X, because the proportional doesn't mean that both the variables are equal. That means that if you multiply it by something or divide by something, that two articles would be equal. And it's not negatively proportional, so we don't divide it. So remember. So the spring constant in the spring constant is a force per unit extension. So this is force per unit extension. If that means K equals F over X. It can be derived from the main formula, that is F equals K times X. So the units are N over M. This is Newton over meters. The spring constant is a measure of how stiff a spring is. So the many other materials such as metal wires also obey Hooke's law. Hooke's law is associated with this initial linear straight part of force extension graph. I mean, till the this limit. You remember from this we learned in the investigating force and extension. This is the graph of force and extension, and there is elastic limits till which there is a linear graph, and Hooke's law is about this part, not about all the parts. For example, parts that's after elastic limit does not obey Hooke's law, so do not confuse these two things. Hooke's law is only till this elastic limit. So objects that obey Hooke's law will return to the original length after being stretched. If they don't return, that they are not obeying Hooke's law, because they may have surpassed their elastic limit. If an object continues to be stretched, can be taken past the limit of proportionality. At this point, object will no longer obey Hooke's law because it have already surpassed its elastic limit and will not return to its original length. So we have a question. Below is a graph that represents force applied to a spring against extension of the spring. So here is graph force and extension. State the name given to point P. Yeah, it's a point till which Hooke's law obeys, and this point is called elastic limit. So second question, use the section of the spring where Hooke's law is obeyed to calculate the spring constant of the spring. So to find spring constant, here we can use part until here. After this part we cannot use anything. So here just we can use any point on the string and use our formula. For example, we can get when the extension is 4. So we go here and here. So this point we are looking for. This point is 6.2, 6.4, 6.6. So this point is 6.6. So now we write it down. F equals 6.6 newtons, and extension equals 4 centimeters. Is it centimeter? So then we had formula F equals extend K. So we have to find K. K equals F over X. So we need to find 6.6 over 4. 6.6 over 4. And that's 1.65 newtons per centimeters. We need to use this and this when we are calculating using this formula. If we have newtons and meters, then we can define it as 1.65 newtons per meters, but for now it's newton per centimeters. So we will move on to the circular motion. This circular motion. The velocity is a vector quantity, as we learned in the previous lessons, and the velocity of an object it is its speed in given direction. So when an object travels along a circular path, its velocity always changes. It speeds up, it slows down, or so the speed of an object moving in the circular might be constant. Speed is always constant, but its direction that's traveling along some point or in a constant orbit, the direction is always changing as the object moves along the circular path. So this means an object moving in a circular motion travels at a constant speed, but it doesn't have constant velocity. Its velocity is always changing because of it might have this constant speed, but it doesn't have this constant direction. So the image below shows an example of famous objects that moves a circular motion with a constant speed but changing direction. So that means it doesn't have this constant velocity. So the International Space Station orbits Earth with a constant speed but always changes its direction, so its velocity is always changing. So as you can see here, it has 60 meters per second. All speed is always same. It's said that this image is not to scale. So as you can see here, it has 76.6 meters per second in here and even here, but it might not, it can't be seen from the picture, but its direction is always changing. When a force acts at 90 degrees to an object's direction of travel, the force will cause the object to change direction. So as you can see here, if it's applied in the 90 degrees, it causes this object to change its direction. If the force continues to act 90 degrees to motion, the object will keep changing its direction, whilst remaining in constant speed, like in the circular motion, and travel in a circle. This happens when the planet orbits a star or satellite orbits planets. As you can see here, when satellite is moving around this Earth, the force is being applied, and this force is gravitational attraction. For example, when moon is moving around Earth, it doesn't just move because it has some source of energy. It is because there is applied force that is gravitational attraction. So the moon is pulled towards Earth at 90 degrees its direction, and because it has speed too, it will keep changing its direction constantly. The force needed to make something follow a circular path depends on the number of factors. So first one is mass of an object. So greater the mass requires the greater force when speed and radius are constant. The speed of the objects. Faster objects will require greater force and when the mass and radius are same, and the radius also. Smaller radius requires the greater force to keep its radius constant. So here the formula for this comes here. So the formula like this. This acceleration of this object equals to gravitational constant. That's about 6.674 times 10 to the power of minus 11 newtons per meter times m divided by a square. So here this is the acceleration of the object that seems to be constant in a speed, but not constant in direction. So g is, as I said, it is gravitational constant. M is the mass of the mass of object that another object is moving around. For example, in our case with Earth and Moon, it is Earth's mass, and r is the radius of moving objects' orbits. So, for example, moon, when we consider moon and Earth, it is moon's orbit. So here, this R is this. For example, in our case with Earth and Moon, it's moon's orbit. So you can use this formula when it's needed. So now, satellite is orbiting around Earth at a constant speed in a circular orbit. Discuss whether satellite is accelerating or not. So to discuss this is accelerating or not, as we learned, um, if something is moving around this something else at in a constant speed, it doesn't mean that it has constant this constant velocity too, and that means it if it doesn't have constant velocity, that means its velocity is accelerating. It can be even accelerating or decelerating, and both of them are considered as acceleration. And this acceleration can be calculated using the formula that I have just shown. So we can say that the satellite is accelerating. So the next one is friction. Friction in solids. Friction is a force that works in opposite to the motion of an object, and this slows down the motion of object that is moving against this friction. When friction is when friction is applied, the energy is transferred in the format of heat. So this raises temperature, thermal energy, it's called also, of the object and its surroundings. So the work done against the friction forces causes this rise in temperature. Friction in solids is caused by imperfections in the surfaces of the objects over one another. For example, sometimes you may see some things as having clear surface, but actually, if you zoom in, they actually don't have clear and this perfect surface. They have always imperfection. For example, even here in this phone, it might seem that it's a really perfect surface, but it actually doesn't have that. When you apply this, it actually tries to slow down your motion. So that's why we can assume that actually most of the things that we think has perfect surfaces actually don't have perfect surfaces. So not only does this slow down the object, but also causes an increase in thermal energy. But if this thing is done with small objects, we may not see the difference in temperature, but actually it does increase thermal energy. So here this force is friction, and weight, direction of the motion. As you can see here, friction is against the direction of the motion. For example, if the motion is going like this, friction is like this. If its motion is up, friction is down. So it's weight of the person. The friction happens because of the way imperfections on the two surfaces at the molecular level push against each other. As you can see here, this seems to be like linear, perfect line, but actually, is when you zoom in, it has imperfections too. So friction in fluids. Gases and liquids are known as fluids. Fluids are different compared to solids because particles can move around, where then this solids they only stay the same. They can only vibrate, and that's it. Friction acts on objects moving through gases and liquids as the particles collide with each other. This type of friction is called also drag. So air resistance is type of friction that slows down the motion of an object. So so as you can see here, rocket's return model. When a rocket leaves the Earth, it leaves its return model too. And sometimes they are planned to go into this oceans. So overall, when it's falling down, the air resistance is doing its work against this motion of this return model. So particles bump into objects as it moves through air. As a result, objects hits up due to work done against the frictional forces. As I mentioned before, they are planned to go into this ocean because this due to this air resistance, when things are thrown from the really high spots, they get really hot until they reach Earth. So that's why if they are planned to go into this some house of people, they can burn that house because the distance between them is really big, and so that's why they are planned to go into oceans, and that's all due to this air resistance. So that's it for today, and we finished this learning effects of forces. In our next classes, we start learning moments. Goodbye, and I will see you later in StudyMates physics class.